handles large amount of I/O tasks and post-processing. So we propose a new in situ visualization software named AWP ODC in situ, which is based on the AWP ODC open source by employing the ParaView and its ParaView Catalyst library. So methodology. The AWP-ODC open source is a CUDA C-based open source scientific modeling software developed by HP GOC Lab at SDSC. This software simulates earthquake by solving elastic wave equations. It uses staggered grid finite difference method at first order, and the computational domain is a structured grid. As we can see from the charts on the bottom left, is that we decompose the whole computational domain into subdomains and feed them into each GPUs and do the calculation on each GPU locally, and then gather the data back into as a one whole model to output to the hard drive in the binary format through MPIO. And also normally we will save like dozens of terabytes of a velocity model result, and then do the post-processing with a separate workflow, which will cost a lot of time and also a lot of resources. So ParaView is an open source, multi-platform data analyze and visualize application, which provide us a solution for in situ visualization to solve this intensive I/O output tasks. Our efforts within this work can be concluded as we redirect the data from GPU memory into a VTK-grade data structure located in the CPU memory. We also developed an adapter code with the ParaView C++ API to pass the VTK-grade data to the ParaView GUI. We also prepare scripts with the ParaView Python API to perform tasks like in situ visualization, movie rendering, and as well as the data output. The implementation, the left-hand side chart is the original AWP-ODC workflow. Basically, after the solver starts to iterate it through each time step, we will have a data buffer in the CPU memory. So once the CPU memory buffer is full, we're gonna write down the data to the storage once with MPIO. In such case, we can reduce the amount of the times to access I/O, to access the hardware storage. So the right-hand side is our updated workflow. Still, because we want to do in situ visualization, which means we want to see the result as soon as possible. So we eliminate the CPU memory buffer. So in this case, each time the GPU downloads the data from CPU download the data from GPU, it will be fed to a co-processing adapter, and then this co-adapting adapter will form a VTK readable structure grid format, which will be passed through ParaView Catalyst library, and we will gonna decide if based on the Python script we write, if it's a in situ visualization script, we're gonna pass the data stream directly to ParaView GUI. If not, we're gonna choose, are we gonna write down the VTK unstructured grid for future visualization, or we can start rendering movie and save save a two-dimensional image with the angle that we set up for each output iteration. So we have for the in situ visualization, we have this small showcase. It's working on desktop with a 4 NVIDIA 1080 Ti GPU and the 1 4-core i7 CPU. For the model, we have a homogeneous model with point source. For the topography, our code can adapt real DEM data for visual effects only, because the AWPODC code is finite difference. It's a traditional finite difference method, so it doesn't. The method itself doesn't take the topography into consideration, and this DEM is only for the visual effects. So this is a screenshot in real time. We can see at the very beginning, in the terminal, I start this AWPODC in situ software, and right now, since it's real-time rendering, so we can change angles, zoom in and zoom out. Also, for this data set, because we save results for velocity along X, Y, and Z axis, so it's a 3 sets of arrays that we can change in real time. This original video is long, have length of 6 minutes. We just, for the presentation purpose, we kind of fast forward a little bit. So let's talk about the benchmark. So first, the benchmark environment is using a machine called Recon, which utilizing the GigaIO FiberX solution. This machine contains one super micro 1U server with one Xeon 16-core CPU with 128 GB of memory, and there's 3 PCIe Gen 3 by 16 lane connection. Each will have 4 NVIDIA 1080 Ti GPUs. Also, this server connected with a Samsung 8 GB NVMe drive in the RAID 0 configuration. The code is compiled with Ubuntu 18.04 with GCC version 7.3, CUDA version 10.0 with OpenMPI 2.1.1. For the remote rendering solution, we're using virtual GL for the three-dimensional acceleration for the remote PyroView GUI, and also using the Turbo VNC to launch the remote desktop. So let's talk about the benchmark result. As we can see from the table from the right-hand side, our AWPODC in situ achieved comparable parallel performance and efficiency compared with the original AWPODC open source implementation. We can see that I need to make some explanation that for the AWPODC open source, we have 2 modes for performance record. One is for no output, which means the software only doing calculation without any storage output. And the binary means this software will save the output data in binary format with MPIO. For our AWPODC in situ, we actually have 3 models. The first one is called grade, which means the code will save exactly same amount of data output as the open source version, and but in the format of VPK, it's unstructured grade point, parallel grade point. And the second movie is for each iteration for output, we're going to save a still an image and save that image to the hard drive rather than the data itself. And the third version is live, which means it's in situ live visualization. So we can see our grid mode often performance is very close to the binary mode of AWPODC open source. And as for the movie mode, our AWPODC in situ is achieved 2100 G-flops of performance. However, this output file, since it's only it's an image, so that's actually this model we saved more than 400 times of storage space to save the visualization data. And also we implement we can see from the chart that we implement the live visualization with a very small overhead if we compare with no output option from the open source version of AWPODC. So in general, both the AWPODC software and the AWPODC in situ software can achieve about 90% of parallel efficiency up to 8 GPUs on Rincon machine. So conclusion and the future work, we developed this AWPODC in situ code to provide the in situ visualization functionality for the AWPODC OS seismic simulation software. We also run some benchmark using this software on a multiple GPU machine. That result shows that our in situ implementation achieve expected performance and efficiency. In addition to continue optimize the I/O operation and the tuning performance, we also plan to benchmark our code on the larger distributed system, since the AWPODC code can run with very high parallel efficiency among hundreds up to thousands of compute nodes, that we want to try out if this code can achieve similar performance on such large distributed computational system. And yes, another goals we also have, like we want to update this code along with AWPODC master branch on GitHub, and also continue optimize the code for better parallel efficiency. Acknowledgement, this work was conducted by SDSC Advanced Technology Lab, SDSC HPGOC Lab, and the GigaIO company. And this paper is published in the conference proceeding with PERC 2019. This paper is also supported by NCSA Innovative System Lab, SDSC Advanced Technology Lab, as well as GigaIO company. And thank you, everyone.
So one of the I'll show you one of the things that we gave Dawei the capability to do, and one of the things that his boss Ron Hawkins asked us to do was, how can we create a system? Could Fabrics help them to create a system that would give them favorable results without spending as much money, right? Or more poignantly, could we achieve the same level of performance at greatly reduced price? And as you'll see from the charts, we actually failed in this regard, because we achieved substantially less performance, less system cost, but we actually achieved greater performance, not just the same. All right, so you know, we got 25% higher performance out of a system that actually cost them, you know, about almost a third. All right, and the effect here is, you know, with fabrics, the ability of being able to establish peer-to-peer relationships between storage and GPUs, and the low latency of the fabric just keeps the GPUs, it gets data to the GPUs faster, and it gets data away from them once calculated. And so you can see here, you know, the effect of this. I think you not see the pointer. Okay. So on the bottom left, we're showing the effect of, you know, what happens in the system in their current configuration of the Comet system. And if you use P100 GPUs, which are relatively expensive, you can see at 1 GPU, but lower is better on that chart. So the blue line shows with 1 GPU, they get about 40 or 50% better computation with their system over ours. And I'll say because we use the 1080 Ti's that Dawei talks about. And so that's the effect of spending $6,500 versus spending $1,000 on the GPU. Now what happens though, it's interesting across fabrics, by the time we've gotten to 4 GPUs, we've caught up in performance. And you can see when we get out to 8 GPUs, we've actually are now running about 20–30% more performance. And that's $8,000 worth of GPUs against, you know, $52,000 worth of GPUs. And we're running faster. And it's because of what you see over on the right-hand side, the utilization of the GPUs. And when you go from 4 to 8, and when as you climb in the number of GPUs, the efficiency and the utilization of the GPUs decreases, but not in fabrics. And you can see when we get out to 8 GPUs, we're still keeping those GPUs utilized over 95% of the time. So, you know, just quite quickly, I'll show how people end up using the system. You can scale up and you can scale out. So we're showing here a couple of switches. They can be, we've got larger configurations. They can be cascaded. You can have, you know, whatever basic topology you want. It can be dragonflies or leaf and spines or whatever. You can attach servers to those. The connection, of course, is PCI Express. You can run MPI applications, and you can put, you know, some number, 20, 30, 50, 100 servers on this and just run it exactly like that. You can also, as Dawei did, you can attach in PCI NVMe storage. And in this case, this is just a JPOP. It's literally just a bunch of flash drives. You attach that to our top of rack switch. You connect the servers to the switch, and you connect the storage to the switch. You could also connect to storage servers. So it doesn't have to be just a bunch of flash. You can also be a storage server. You can be running NVMe OF. And so now you can make that storage as large as you want. You can connect to as many servers as you want using very classic and common NVMe OF storage. And what we do in storage, we can do the same thing over on the GPU side. So you can connect to a bunch of GPUs that are sitting in a box, or you can connect to a GPU server that has a bunch of GPUs, and now you can share them. And in fact, what you put in the JBOD, you can put in anything. It can be just a bunch of anything. If it connects to a PCI, you can stick them in the box and you can now share them across the network. And when you think about it, PCI Express is in fact a memory semantic network. So you can do loads and stores directly across the network. And so we can support storage class memory or persistent memory shared pools today. So, you know, the benefits that we see out of the collaboration, you know, as Dawei talked about, you know, from a science standpoint, he got a low-cost sandbox, right? We gave him a tool to be able to play in, and Dawei did quite a bit with it. I think we get, you know, better science at a better time to solution and so on. From GigIO's perspective, we've tremendously enjoyed the interaction with San Diego Super and with Dawei, and we'll continue to do that. You know, for us, it's really important to get real-world test results, and to listen to people like Dawei and others who know what they're talking about, what they really want to do with our system, and hopefully we end up making a more robust solution. So we want to thank, you know, Ron and Dawei for participating with us, and we were happy to do it. So with that, we'll open it up for whatever questions that you might have.
Yeah, let's take this. additional questions, if you can use the microphones there, I appreciate it. Or there's a portable one too.
I will come to the microphone.
All right. You almost remember.
Could you describe the reference case of the non-fabrics connected system? Because it would seem that you wouldn't have an InfiniBand connection with one CPU and up to potentially 4 GPUs that you could a server or already be PCI Express connected or NVMe connected. So what were you comparing against? What does that look like? And I'm just curious why you got such bad results on the InfiniBand base case, even at a low number of CPUs.
So the Comet system is based on 4 GPUs per server, right? It's 2 GPUs per processor, 2 processors per server, so there's 4 GPUs. And so the base case was 3 servers. Yeah, it was three servers. And so there were 6 processors and there were 12 GPUs. And what we really found in the course of doing this work with Dawei was that we gave him effectively the knobs to be able to precisely tune in how many GPUs could he put onto a processor. And it turned out that in this particular software, and I'll say it's not necessarily true for all, but in this particular case, the processors actually don't do a lot. And it turns out that the processors are really babysitting the GPUs, and so we gave him the capability of being able to play, and he found out that a processor can handle 12 GPUs, and so that's why it ends up looking like that.
Other questions? I have one. I'll go to the mic. So you're running these out and you're bypassing InfiniBand. What do you have requirements about error rates or latency in the physical transfer of that?
Ask your question one more time.
So the connection, because there's error correction and things that are built into InfiniBand.
Right.
If you're bypassing that, what happens if you have errors in the transmission?
Okay. So it turned, as you might, hopefully expect, PCI actually has a pretty robust environment in terms of what it expects in terms of error correction and the quality of service that's built into PCI. And so we effectively take that across the network itself. And so the main way that it shows up with PCI is around distance limitations, right? So there's certain timing that has to happen, and so you can set quality of service with you either do a weighted a round robin or a weighted round robin methodology. And so if you take it out, speed of light still has speed, and so we can support out to about 100 meters before you won't get the timing that's required to do that. But aside from that, the quality of service across the PCI network is built in by PCI, and we just take advantage of that.
Good, thanks. All right, other questions?